we're going to go ahead and get started. So to get going with it, go ahead and make your way to cosyne.sleep.ai on your browser. And I'm going to show you what that looks like. You're going to, whoops, okay, let's switch over here. Okay. As you go to cosyne.sleep.ai, we've put together this tutorial website, which is intended to kind of guide you through several short steps. These are essentially only going to take a couple of minutes each, so we're likely not even going to use the entire rest of the time, and we'll be walking around to help you get started. But the very first step here will essentially be just to get yourself set up. And because Sleep uses GPUs, and you might not have a GPU on your laptop right now, one of the things that we've done to make this a little bit more practical is we have set up a number of virtual machines running on the cloud that already come with Sleep pre-installed and have GPUs in them. So I'm going to just walk through this process of setting up your VM, but once again, it's going to be really, really easy. The idea is that you're going to start off by opening Chrome Remote Desktop. That's this guy here. You're just going to go to remotedesktop.google.com or click this link. All you need is a Google account. And what Chrome Remote Desktop gives you is essentially a way to connect to a remote computer. And so in order to connect to your own virtual machine, what you're going to do is click over here to set up via SSH. You're going to then set up another computer by clicking on Begin. Ignore all of these links here. I'm going to zoom in, just make sure people can see. You're going to click Next, Authorize, and you're going to land on this page here that has a few different commands for you to copy. Go ahead, and once you get to this page, click this button to copy to clipboard the code for Linux. And then you can scroll down. And what you're going to do is you're going to go to this VM request website. The link is, once again, in the setup page of cosyne.sleep.ai. Yeah, sorry. Again, you're totally going to be able to do this by yourself. I just want to show you this next step, because it's really just one quick thing, which is copy this code from here, go over on this form, and type in your email, and then paste that command, right? Just like that. Type in your email, type in that command that came from Chrome Remote Desktop, hit submit, and you'll get a success page that looks like this. Okay? Now, when you go back over to Chrome Remote Desktop and you click on Remote Access, you'll see that a new virtual machine, a new device has appeared. This is now, for the next couple of hours, your own computer that only you have access to. You can just click on that guy. It won't show for me, but for you, in the first time you connect, it'll ask you to type in a PIN. The PIN is just 1, 2, 3, 4, 5, 6. Don't tell anyone. Of course, this PIN does not matter whatsoever because you are the only person who has access to this VM. We can't access your VMs. Technically, we can't. We won't. Once you access your VM, you'll land on this page here, which is essentially a new desktop, a new virtual machine. If you go to full screen, you'll be able to work on it. And if you click on Google Chrome, you can go back to this web page so you can keep following along with the guide. And you can basically skip to step 2. So recapping once again, all you're going to do is, in the tutorial, it has pretty thorough screenshots showing you step by step how to set up your Chrome Remote Desktop. Click, 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 copy this code, go on our request website, get your virtual machine, and then go back to Chrome Remote Desktop, where you now will have access to this virtual machine that is running on the cloud. From there, you can already continue to step 2, in which you're essentially just going to open Sleep. And the way that you're going to do that is by going to desktop here, this folder, you right-click, open terminal, and you're just going to type the magic command. This is the only command you're going to type this whole tutorial. Just write sleep-label, press enter, and momentarily the sleep interface will appear. So I know that might have been a little bit fast, so we will recap this in just a moment, but I'll give you guys a minute to step through the tutorial. But once again, just refer to the tutorial website. It should guide you through every step. And we'll walk around for a couple minutes here to make sure everybody's set up. If you're having any issues, just please raise your hand. One of the circulating TAs will come by and help you. All right, I hope everyone's doing well and have been able to get into your virtual machine. Feel free to keep working through it in your own pace, but I just wanted to walk through one of the next steps just so that we have something to look at up here in the screen. And what I'm going to do is I'm going to just start training one of our basic models. So feel free to follow along the screen if you want, or if you're in your own flow, just ignore me. But what we're going to be doing here is importing one of our test videos here, this video of our home cage mice collected against a very overexposed illumination setting. What we're going to do is we're going to add these 3 nodes here: head, torso, and the tail base, because that's basically what a mouse is, right? Who needs more key points than that? Not I say. We're going to generate a set of labeling suggestions. So the labeling suggestions are essentially just a feature. It's totally optional, but we highly recommend that folks use. It just sets up a list of frames for you to annotate. Some of the methods actually use more advanced approaches to select frames that are more ideally useful, but we're just going to sample a bunch of frames that are spaced out in time. And we're just going to label one frame, namely this frame 1411. It's a magic frame, which happened to be a random one that I clicked when I was writing the tutorial. And we're going to label this frame by right-clicking, selecting default. Then I'm going to click and position all of these nodes roughly where they should be placed. The torso is not really a single key point, but rather a whole structure. So we're just going to kind of ballpark where we think it should kind of go. And that's where it's going to go. Awesome. I'm going to go to File, Save, and save my SLP file. This is our project. And then we're going to go on to the next step. So as you can see, each one of these 9 steps, which seems like a lot, really only take 1 or 2 minutes each. And we're now going to train a model that only has a couple of settings that aren't the default, and they're really just adjusted for the purposes of this tutorial. But let's see what happens. I think I tried this a couple of times, but let's see how reproducible this really is. And so for those curious about what's going to happen here, what we're doing is we're training a neural network totally from scratch, or really 2 neural networks, because this is going to be a top-down approach. We're going to tune this guy to have first the sigma for centroids of 3, anchor part being the torso. And you can click these little plus signs here if you want to understand what these settings are doing. Put a little bit of fun theory there if you feel like you weren't learning enough just by doing. All right, so this resolution is a little bit unfortunate because of the projection system here, but that's okay. We'll manage. So 3, torso. I'm going to scroll down. All right, we're going to configure just a couple of settings on this next tab. We're going to make the images a bit smaller. So I'm going to click this guy here, scale it to 0.25. That means that we're going to process the images at 1/4 of their original resolution. This is because we can get away with pretty coarse resolution images for just detecting centroids. We're going to set this to, rather than 200, it's just going to do 5 epochs. An epoch is a whole round across the data set, which in our case is a single image. Because once again, we are training a UNet-based backbone. We didn't really get a chance to talk too much about the UNet and the network architecture design in SLEAP, but suffice to say that these are all pretty custom neural networks. They're initialized totally randomly. These are random weights. It's never seen any data. We're just literally just sampling from a Gaussian distribution to set the initial weights. So this is as naive of a neural network as it gets. We're then, we set a couple augmentation parameters, namely the main augmentation we tend to use is just rotation. We find that's a strong enough augmentation to enhance generalizability. We're going to click over to the centered instance model, and then we are going to set epochs to 5 and the rotation angle once again, to minus 180 to 180. And what SLEAP does is every time it grabs an image from your data set, it will apply these random augmentations, where here, when we only have rotation enabled, what it's doing is it's just randomly rotating the image and adjusting the labels accordingly. So even though we only have a single labeled image, it's in effect generating many variants of that single image. That's going to be one of the tricks that's important. So I'm going to hit run here, and right away, what we're going to see is this training model window appears. It says it's preparing to run training. And if you're curious, you can actually look at the terminal and see there's a bunch of stuff getting spit out, which is essentially SLEAP setting up everything from the data pipelines, a bunch of optimizations, preloading, creating the neural network, setting up checkpointing, setting up logging, all sorts of fun stuff that happens under the hood. And then eventually it'll start to actually train, which you'll see here with the runtime counter starting to tick away. And then soon you'll see that all these dots begin to appear. Each one of these dots is a batch. A batch we right now have configured to be 4 images. And what SLEAP is doing is it's taking 4 images, in this case 4 variants of the same image, of this one frame that we labeled, applying a bunch of random rotations to it, and training the network to try to predict those heat maps, those confidence maps. And what you're seeing is that the loss, in other words, the objective function or how well we're doing, is going down. And by going down, I mean the error is going down, right? And you can see that it's going pretty smoothly down, where each dot here is, again, a set of 4 images. Once again, it's essentially the same 4 images. And what we're seeing up here on the right is a preview, a visualization of those heat maps, where the green points are the ground truth locations that we just labeled, and the red points are the predictions, where it's guessing. And what you can also see overlaid are those heat maps, which are currently how it's trying to guess. And already you can see how this builds some insight into how the neural network is learning, right? Like, even though we actually are training it against predicting like a perfectly spherical Gaussian, essentially like a round heat map, you can see that it learns a little bit more of an elliptical shape. And the reason for that is that it's because it's still learning what a mouse looks like. And because mice tend to be a little bit longer, right, there's still some ambiguity about precisely where that torso key point is. So as it's learning to deal with that ambiguity, it's essentially, learning to de-elongate that confidence map. And I mention this because I've stared at these previews of how it's doing for way too long, and I'm very, very curious about how these neural networks actually learn. I think there's a lot that can be still learned about how neural network optimization works in a general sense, just by visualizing and understanding the dynamics of optimization. So if there's anyone theory inclined and looking for a job in which you're going to be doing some neural network theory, definitely reach out. These are also just fun to look at. So, all right, that model finished training. It probably took around a minute or so. There's a bit of downtime, and then now it's starting to train the second stage of the top-down method, which is the centered instance model. This is the one that takes a crop of the animal and tries to predict the other key points at high resolution. And in a moment, we're going to see, there we go, a preview of the confidence maps for the centered animal. And what you can see is that, once again, even after just one epoch, it's already doing quite well. And you might say, yeah, is it surprising that it's doing well? We're training on one image, and it's doing a very good job at that one image. Because ultimately, we have now essentially 2 neural networks, each with a couple of million parameters, which for neural networks is actually fairly small, right? These larger language models have something on the order of billions of parameters. So these are fairly modest ones. But nonetheless, millions of parameters, much more than your father's linear regressions and support vector machine kernels and so on. But nonetheless, one that is still quite a lot of parameters to learn from a single image. So once again, it'll go through this. It'll probably take about a minute. And then it'll begin to predict. So I'm going to close out these little preview windows. We don't need them. In a moment, this will start to, oh, shoot, I should probably not have done that. Do you terminate? No. Sorry. Won't touch that. It is, there you go, setting up prediction. And now it's running that on all of the remaining images in our labeled suggestions. Boom, it ran inference on 49 frames. 43 of them had predictions. 6, it just failed. And let's see what our predictions look like. OK, so here are the predicted poses in one frame. It doesn't look that great, but it's at least on the animals. That one failed entirely. That one's pretty good. That one's OK. That one failed. That one's actually pretty good. Consider, again, the fact that this is the only image that our neural network has ever seen. Its only knowledge of what a mouse looks like comes from this single image. And yet, it's able to still do a reasonable job at predicting the general structure of the pose of a mouse that is literally in it's a spatchcock jump type pose that is in a very much different size, shape, and scale. And if you go through it, some of these predictions are actually quite excellent. I mean, this one's pretty much perfect. This one's pretty much perfect. Oh, this is actually quite surprising to me. I hadn't gotten this result before. I'll remind you one more time. This is a network that is trained with completely random weights. We're not transfer learning. It's never seen any images before. It certainly has never seen mouse images. It only saw that one image where there were 2 mice and they weren't even facing each other. And yet, it's able to generalize fairly reasonably well to another image in which we have 2 mice, they're in a different location, they're in a different pose, and they're even facing and touching each other. And it's already doing a pretty decent job at predicting that location. But it's not perfect. So this is where the human in the loop part comes in. You're just going to double click one of these guys, and I'm just going to correct the location of the head, adjust the torso a little bit. And this guy's already perfect, so I'm just going to leave him as is. And now, ta-da, I've labeled a second frame. And all it needed to do is double click the predictions and slightly correct it. And I'm done labeling a second frame. What you're going to be doing is essentially going through and clicking on a lot of these. Like, wow, this model really actually performed quite well. Yeah, in all my testing, they were doing OK, but not quite this well. This is good. In any case, I think this is intended to kind of give you an idea of how well SLEAP can perform, even with very little data. Even in the limit, literally one image, and then generalize to other images that look somewhat similar. And really what we're pushing it against is the boundary of, like, what does it mean to learn the concept of a mouse head, of a mouse body, and so forth. And as we mentioned in the talk, a lot of this has really only it's only possible because we built in all of these inductive biases to ensure that these networks can learn in this sort of sample-efficient regime. All right, I'm going to leave this up for a second, and we'll come back a little bit later to do inference. But why don't you guys go ahead, and you should be able to get through to this step, which should be step 4. And then step 5, where if you get all the way to this point, I would recommend labeling a few more, maybe around 15 to 20, as you go to the next step. But what I hope you can appreciate is the fact that it only takes a couple of minutes to train these lightweight models, and they generalize remarkably well. They perform remarkably well on frames it hasn't seen, therefore making it much faster for you to label new frames, as you'll appreciate once you're starting to label from predictions in step 5. And once again, feel free to raise your hand if you're running into any issues. All right, I hope everyone is progressing well with training their amazing models. We have about 15 minutes or so left technically in the session. No one's going to kick you out, or maybe they will. In any case, I just wanted to have a couple of closing thoughts and remarks and highlight in case you haven't quite gotten to it. A couple of practical things. One is just that, so we built this website here, cosyne.sleep.ai, specifically for today's tutorial, but I see. Okay, let's try that again. Great. So we built this website here, cosyne.sleep.ai, specifically for today's tutorial. We hope you liked it. It took us a lot of effort, but hopefully things went smoothly. We will be doing future tutorials at a bunch of other venues. Probably the next major one will be back here at Champali Mode for the Cahal course on quantitative methods for behavior, or some mix of those words. I think the deadline to apply to that summer school is soon, if not past. Hopefully, okay, not fast. Good. Soon. So if you guys want to learn more about the stuff that we're doing, and importantly, all the other folks in the fields, tools, it should be a lot of fun happening this summer. There's also another course at Jackson Labs that happens in the fall, if you happen to miss that one, that also brings together a lot of really cool folks in this community. I want to point out a couple of more follow-ups here. One is this section here called I'm Done Sleeping, Now What?, which kind of walks you through what happens after you run through sleep, which hopefully you'll have appreciated is ideally one of the easier steps in the whole workflow. I think you saw it, you're able to, in a single sitting here, go from having a raw video to a trained model that's reasonably performant. And so on this page, we have a couple of notebooks showing how to actually work with the sleep data that's output. You can open them in Colab and just get a sense of how to use different formats. We especially recommend and I would like to highlight Neurodata Without Borders. This is a standardized data format for all sorts of different data types, and we really would like more folks to adopt it and improve the reusability of data that's produced out of softwares like Sleep and others. But we also have lots of integrations because we don't just, Sleep doesn't work in isolation. It ends at the point of having a bunch of key points, a bunch of poses. In order to make some sense of it, you'll probably want to do something like behavior segmentation. And we list out a whole bunch of different tools here that are compatible directly with Sleep in some way or another, mostly by just taking Sleep outputs as inputs to their own pipelines. I especially would like to highlight Keypoint MoSeek, which you guys saw several examples of in the talk today. It is a really well-developed toolkit for unsupervised behavior segmentation. We've had lots of success using it ourselves for our own uses, and lots of folks that use Sleep have been having a good time using it. Whereas on the supervised side, there's a few different options here that you can check out, and they all have their own different approaches for doing supervised behavior segmentation. There's a few other utility libraries that also are more practical. So if you're a tool developer and you want to understand how to build integrations, Sleep, the main Sleep package itself is really kind of a little bit more intended to be standalone and running in its own environment. But if you'd like your tool to use Sleep in some way, if it just uses Sleep data, we built a standalone library called Sleep.io that allows you to load and write Sleep files in our native format, as well as convert from other formats that store pose data. And it can be a really easy way to just allow your program to just be able to ingest the outputs from Sleep. As well as index pose, or NWB, which is, again, another standard format, and this movement library, which I've been a kind of a big fan of. They also serve this use case of taking in a whole bunch of different pose estimation software's outputs and essentially running different kinds of analyses on it, which once again is going to be one of the next steps of what you do once you have your pose data. And then we also include here a bunch of different papers if you want to start your journey towards learning more about how this stuff works. In particular, I'll highlight this Nature Neuroscience review that we wrote a few years ago. It's still quite, I think, timely and covers the general concepts that we talked about today of these different levels of behavioral quantification and tracking, as well as what you do with the outputs. In particular, highlighting some of the use cases of how you actually link behavior to the study of the brain, such as and including some of the more neuro-AI-oriented applications that we've been talking about towards the end there. We also include a few different links to different subfields that have been employing these approaches and kind of review how you can use it for your own needs in if you're doing things like studying everything from pain to general purpose home cage monitoring to rodents largely, social and affective behavior, and even humans. And finally, I just want to encourage you all to just do this survey over here, which, oh shoot, I'm not logged into my Google account, so I will open it over here, where if you have a second to take this survey, it's a very short Google form that, I swear Google, it is me. Don't look at my password. Now you know how long it is. And essentially, it's really, really short. It's just going to ask you for a couple pieces of information, such as, and namely what we really want to know is, can we reach out to you to distribute general news and updates related to sleep? But more importantly, we'd really appreciate folks who would be interested in checking off the second box here of folks interested in beta testing new software that makes post-estimation and behavior analysis easier. And I'll be very, very transparent. This is for reporting for a grant in which we're establishing a user base of beta testers who are going to be helping us to develop the next generation of sleep that has all sorts of cool new functionalities and which extends some of the capabilities that we built for the tutorial today. Although I won't blame you if you don't want to get more emails. Finally, we did promise some free swag and shirts and stuff. You'll see some of our TAs walking around with sleep shirts already. We didn't get a chance to finish printing the new batch of shirts to bring here to Cosyne, but we're happy to mail them out. And in exchange, all we're asking for is that you upload an SLP file from the tutorial today. And we will actually use that as data to inform some of our research into data annotation variability and to help calibrate our models. If you just upload a dummy sleep file, that's kind of okay as well. We'll send you something just as a thank you for coming to the tutorial. And if you have any other comments and feedback, we'd love to hear more about it. And we may be hiring across different positions if you're interested in this kind of work. So thanks, everyone. We still have a few minutes. We'll be around here, but thanks again. Yeah. And I will leave this guy up here. Oh, nope. Yeah, I think this one's pretty good. It's a good note to leave this on.